Okay, so welcome back to this video on why the LP space is a complete metric space. So what we've shown so far is that if we take a sequence of sequences in LP, so a sequence of sequences in LP, and that sequence is going to be a Cauchy sequence in LP, then it implies that this sequence of sequences has a termwise limit, i.e. each of the termwise sequences is going to be convergent and is going to converge to some value xi. What we now want to show is that, firstly what we need to show is that this sequence is in fact an element of LP, i.e. that it is within the metric space, and secondly what we need to show is that this sequence of sequences in fact does converge to this sequence in the metric of LP, i.e. with the DP metric. Okay, so we're going to actually do those in the opposite order. We're going to show the convergence criterion first, and then use the fact that it converges to show that it must be an element of LP. And once we have both of those together, we'll have shown that it does indeed converge to something within the metric space, basically. Okay, so firstly let's begin with the convergence criterion. So, if this sequence of sequences is going to converge within LP, then what it means is that, well, firstly actually let me just say something. If it's going to converge in LP, then it's the absolute best hope we have of something that it's going to converge to is this sequence, which we haven't even proven is in LP yet. But if it's going to converge in LP, it's going to converge to its termwise limit. This is its termwise limit. So if it converges to this, basically. So if this does converge, what is the definition, what is the criterion for convergence? It means that for all epsilon you give me greater than 0, there should exist a point, a big N, which is an element of the natural numbers, such that if little n is greater than or equal to big N, it implies that the distance in the LP metric space, this dp, of the sequence x little n to this sequence x, which we think is going to be the limit of this sequence, should be less than epsilon, i.e. there should exist some point in the sequence of sequences such that if you take any sequence beyond that point in this sequence of sequences, and ask what's the distance of that sequence to the thing that we think is going to be the limit, that should be less than epsilon. We should be able to find a point for all epsilon such that this is true. Okay, so what we need to do is say, given an epsilon, we need to be able to do this. Well, let's firstly fill in what the distance between a sequence x little n and the sequence x is. So this distance in the LP metric space is just defined to be the sum from I is equal to 1 to infinity of the modulus of x ni. So remember, the n goes into the superscript and the I denotes the term of the sequence. And once again, I'm going to replace this dummy variable with r, minus xr, because I'm just likely to use I later on for something to mean a specific term. Okay, so to the power of p, and then you take 1 over p of that, that is going to be less than epsilon. So that's just the definition of the LP metric, basically. So you ask what's the difference between the nth term, what have I got here? The rth term of the nth sequence and the rth term of the termwise limit sequence. You take the modulus of that, do it to the power of p, sum it up for every single term, what is equal to 1 to infinity, and then take that sum and do it to the power of 1 over p, and that's going to be less than epsilon, basically. If convergence holds, and that will be true for all little n greater, well, it needs to be true for all little n is greater than or equal to some big N. Okay, so what we're going to do is firstly bring the 1 over p to the other side by raising both sides to the power of p. So we'll get the sum from r is equal to 1 to infinity, the modulus of x n r minus xr to the power of p needs to be less than epsilon over to the power of p, rather. Okay, and basically what we're going to do is we're going to get this from the Cauchy criterion that we already know is true. So let me get another piece of paper. What we know is we know the Cauchy criterion. So firstly, can I just formalize something? Let's say let epsilon be greater than 0. Okay, so what I'm now going to do is I'm going to say, okay, let a new variable, let eta be any number that is greater than 0 such that eta is less than epsilon. So basically, if I draw a picture, here is 0. You have picked some epsilon that is greater than 0. I can always find you another number, eta, which is less than epsilon, but still greater than 0, basically. So that's what I need you to find, some eta, which I've labelled pink there. Okay, the middle point. So I need you to find, if you give me any epsilon, I can find you an eta which is greater than 0, but still less than that epsilon. Okay, right. Now, what we're going to do is apply the Cauchy criterion for this number eta, which is strictly less than epsilon, but still greater than 0. Okay, so I'm going to apply the Cauchy criterion. This sequence of sequences, remember, so our sequence S, which was a sequence of sequences, x1, x2, x3, etc. And I'll get... can I get rid of that yet? I will get rid of that for now. So this sequence of sequences, S, which was x1, x2, x3, x4, this was a Cauchy sequence, and that means that if I give you this eta, so eta is greater than 0, I can find you, there exists some big N, which will depend obviously on eta, so it'll be a function of eta, it'll be specific to eta, which is an element of the natural numbers, such that if, what should I call them, if little p and little q are greater than or equal to n big eta, basically, then it's going to imply that the distance, oh dear, and I've put the p down there, let's change this p, let's use the letter m, the dp of the sequence x little m to x little q is going to be less than eta, strictly less than eta. Okay, so what does that mean? Well, remember xm and xq, which are both beyond this x big N, which depends on eta, they are both sequences in their own right. So we have this sequence xm1, xm2, etc., xm3, and then we have this sequence xq, which is xq1, xq2, let me just move this up, xq2, xq3, etc. Okay, and this distance in the LP metric space between this sequence xm and this sequence xq, this distance in the LP metric space between the sequence xm and the sequence xq is defined to be the sum from r is equal to 1 to infinity of the modulus of xm r minus xq r to the power of p, all of that to the power of 1 over p. And basically, I can make that less than eta, okay? So, what that means is, if I raise both sides to the power of p, I can make the sum from r is equal to 1 to infinity of the modulus of xmr minus xqr to the power of p less than eta to the power of p by making m and q greater than this big N, which is specific to eta here. Okay, now what is sure is that the sum, the finite sum, from r is equal to 1 to some, what letter shall I use now, to some big A, let's say, of the modulus of xmr minus xqr to the power of p is less than or equal to this sum here, is what's important now. So this is this infinite sum. So remember what this means. This means the sum from r is equal to 1 to infinity. So we start off with r is equal to 1, xm1 minus xn1 to the power of p. We then add that on to r is equal to 2, which is xm2 minus xn2 to the power of p, plus, and you go on, and eventually you'll get to this big A, which is just some natural number. So you'll have x little m big A minus x little n big A to the power of p, and then you'll obviously go on and on and on. So that's that infinite series, and it goes on and on and on and on. Okay, and it converges on something, basically. Okay, because both of these are elements of LP, these two sequences, xm and xn, xm and xq rather. Okay, so this infinite sum is going to be greater than or equal to the finite sum. So this finite sum on this side here is just the sum up to this big eighth term, and I've whereas this infinite sum goes beyond that big eighth term and goes on further. So this is assuredly going to be less than or equal to this, because this series is of all non-negative terms. So the very worst case scenario is that all the terms after this big A term are equal to 0, and therefore, in fact, this sum is equal to this sum. In all other circumstances, one of them will be positive, will be non-zero, and therefore this one will be greater than this one. And that's because the modular sign turns everything positive, well, turns everything non-negative, and raising to the power of p keeps everything non-negative, basically. Okay, so this is the sum of non-negative numbers. Right, so what we can now say is that for all a is an element of the natural numbers, it is true that this is less than this. So I can make a whatever number I want. It can be 1, it can be 2, it can be 1 billion, it can be 1 trillion. Whatever you want it to be, this statement is true. And therefore, because of transitivity, it implies that this is strictly less than eta to the power of p. So what we get from this is that the sum from r is equal to 1 to a of the modulus of xmr minus xqr to the power of p is going to be less than eta to the power of p. Okay, right, now you might be wondering, why have I done that? Yes, you can do that, you can't stop me doing that, but why have I done that? And the reason is that I now want to take the limit of this sequence. I want to take the limit of this series as, as q approaches 0, as q approaches infinity. I want to take the limit of this sum as q approaches 0, okay? And basically, this may look a very, very complicated sequence, but it is a sequence. Q can equal any number. Q can equal any number beyond big N eta, basically. I chose big N, little m, and little q so that they were beyond big N eta. But beyond that, I can let q equal whatever I want. So I will get a sequence, basically. I can start off with q is equal to big N eta. Then I can take big N eta minus 1. I can build that sequence, basically, of values where you fix m, and you fix big A, and obviously you fix p, and then you sum over r, so it's a dummy variable. But that forms me a sequence, and basically what I'm now doing is taking the limit of that sequence. Okay, so understand why that is a sequence of terms within Q, basically. Q can vary over all the natural numbers from n big eta onwards. Imagine m and a and r, sorry, not r, m and a and p are all fixed parameters now, and q is what is varying, and this sum that the number you're going to get from this sum is going to depend on what q you put in, and we'll get a sequence of real numbers. And basically what we now want to do is take the limit of that sequence. Okay, and why did we convert this from being a infinite series to being a finite series here? Because we can now interchange the order of taking the limit and the sum, whereas interchanging the order of taking the limit and the sum is an analytic nightmare otherwise. So we don't. That's why we've turned it into a finite series, so that we can analyze this limit more easily, whereas we can't with the infinite series, not without some hideous analysis. Okay, and what's also important is that whatever you make q, it is going to be less than eta over p. Therefore, if you take the limit of this sequence, it's going to be less than or equal to eta over p. So basically, if you view this great big series as being a sequence in Q, so we've got some real numbers, it's a sequence of real numbers, like so, and all of those real numbers are guaranteed to be strictly less than eta over p. So if I draw you a picture, here is eta over p, and as Q varies, as Q grows and grows, you've got some sequence, but all of the terms are basically going to be below this eta to the power of p. And the worst possible case scenario is that when we take the limit of this sequence, it could actually converge up to eta of p. So the limit could actually be equal to eta over p. So for instance, to give you an example of that, if we have the series negative 1 over n, basically, as n goes from 1 to infinity, so n is an element of natural numbers, then when you start off with n is equal to 1, you'll have negative 1. Then it will go down to negative a half with 2. And all of these terms are strictly less than 0. Strictly less than 0. So negative 1 over n is strictly less than 0, but the limit of this is actually equal to 0. So the limit in this case could actually be equal to eta over p. So that is why we have done this trick up here by saying, okay, start off with this epsilon, construct this eta so that it's going to be strictly less than epsilon, because then if we get this less than or equal to eta over p, what's going to happen basically is we're going to get the whole thing out to be less than or equal to eta, and then we can say, okay, eta is strictly less than epsilon, so we get that the whole thing is strictly less than epsilon. That's why we went through that kerfuffle of constructing the eta in that way. Okay, right, now, let's analyse this sum. Now, because this is a finite sum like this, the limit of this sum, the order of the limiting process in the sum can be interchanged, because the limit of a sum is the sum of the limits, basically, is a basic theorem from real analysis. So, we can interchange the order of this finite summation, and that's very important. Interchanging the order of an infinite summation and a limit is not trivial, but interchanging the order of a finite sum and a limiting process is trivial. So then we're taking the sum of the limit of the terms of the sum, so the modulus of xmr minus xqr to the power of p, okay? And we now know that that's going to be less than or equal to eta to the power of p. Okay, more paper. Not that. So onwards we go. So now what we can say is that what we want to do is analyse the limit of this. Well, basically, multiplying, raising to the power of p can interchange with the order of the limit. So basically, this becomes the summation from r is equal to 1 to a of let's say, bracket limit as r approaches infinity. Sorry, what's happened there? Q approaches infinity, of the modulus of xmr minus xqr, and then all of that to the power of p, basically, and that's going to be less than or equal to eta to the power of p. And now the limit of this sequence here is in fact just equal to, basically you can interchange the order of the modulus sign and the limit, and then what we've just got is the sum of two things. Yes, okay, it's a plus and minus, but it's still the sum of two things, so we can split it up into the limit of both of these terms. So let me do that. It'll break down into the sum from r is equal to 1 to a of the modulus of the limit as q approaches infinity of xmr minus the limit as q approaches infinity of xqr. And all of this is just theorems from real analysis. To the power of p is going to be less than or equal to eta to the power of p, like that. Okay, let me bring this up now. So, now what we can say is, okay, this doesn't depend on q, so this is just a constant as far as that limiting process is concerned, so this is just xmr. Now, what's the limit of this as q approaches infinity? Well, what are we asking there? So if we go back, if I spell it out, what we're asking is, if you start off with, let's say, q starts off with eta as a function, big N as a function of eta. So if you think about this as a sequence in q, then q can start off at values of big N of eta, where that big N was the starting point for the Cauchy criterion, and then r isn't varying, and then it will go on to x n eta plus 1 r, x n eta plus 2 r. So basically you are keeping the same term in the sequences, but you're going down the sequences. So basically what we're doing is you've gone along to the rth sequence, if you like, and you are taking the limit of that sequence from, I don't know if that's the right picture. No, that's not the right, where did I put the picture I want? Okay, I don't know where I've put that picture that I had. Never mind. But basically, it's a termwise sequence. It's the limit of the half termwise sequence, basically. So that is what this is going to become. It's going to become the limit of the half termwise sequence. So this is just going to be XR, basically. I don't think I've made that clear enough. Let me just draw a picture to make it clearer. So if we write out our old picture. So here is our sequence S, which is a sequence of sequences. So we have x1, x2, x3, okay, and those were sequences. So x1, 1, the first term of the first sequence, x1, 2, x1, 3. Then we had x1, x2, 1, the first term of the second sequence, x2, 2, x2, 3, etc. Then we had x3, 1, x3, 2, x3, 3. Okay, and then somewhere we had x1R, x2R, x3R, so the half terms of all of these sequences. Now, we said, okay, we were applying the Cauchy criterion of the, this was a sequence of Cauchy, this was a Cauchy sequence in LP. So this sequence of sequences was Cauchy. So there was some x big N which was a function of eta, such that if you went beyond that, if you went to x little m or x little q, then the distance between them in the LP metric space was less than eta. So this sequence was xn eta 1, xn eta 2, etc. And then it went all the way down to xn eta r. Okay, and then we had the sequence xq, let's say down here, which could take q could be any value from n eta onwards. So basically, xq1, xq2. So if we draw out this sequence here, xq3. So q, when we take the limit of this sequence here, if we take the limit of this sequence as q gets bigger and bigger, what we're effectively doing is taking the limit of this termwise sequence here, and we know that this sequence of sequences converges termwise. That's what we've shown in the previous video, and we defined that termwise sequence to be the sequence x, which was x1, x, oh dear, and that's awfully confusing the way I've got the x1, x2. Sorry, I didn't realise that. Let's make some new notation up here. Is that going to be confusing? It probably is, but I'm going to make some new notation. Let's call the limiting sequence L, and let's relabel it L1, L2, all the way down to LR. That should have been, not 3, QR. Right, okay, let me just bring this up. So, I've relabeled this sequence of termwise limits as the L sequence, and the reason I've done that is because they were originally called x1, x2, but that's awfully confusing with these. Those were the names of the sequences. Oh dear. Right. So what I can basically now label this limit as is it's the half term of this termwise limiting sequence here. So it's LR basically. Right. So now let's replace that out with what it is. We've got that the summation from r is equal to 1 to a of the modulus of xmr minus lr to the power of p is going to be less than or equal to eta p, and that is true for all a is an element of the natural numbers. So remember, I could have chosen this this a to which I'm summing up this the amount of the infinite sum which I'm going to choose to keep. That was arbitrary. It could be any natural number you like. That was arbitrary. Also remember that m, this the way I got this m, remember, was that m was any old number that was greater than n eta. Okay, right. So now what we wanted to prove, what we were trying all along to prove, was that this sequence of sequences converges to this sequence L in the metric of the LP space. So we wanted to prove that we'd been given an epsilon, remember? So we had our epsilon, which was greater than 0. We wanted to show that there existed a big N, which is an element of the natural numbers, such that if little n is greater than or equal to big N, the distance in the LP metric space between the nth sequence of the of the sequence of sequences, and this limiting sequence L, this sequence of term-wise limits, was less than epsilon. And if we just replace this with what the definition of distance in the LP metric space is, this means that the sum from r is equal to 1 to infinity of the modulus of x nr minus lr to the power of p, all of that to the power of 1 over p, needs to be less than epsilon. Okay, right. But this is true for an arbitrary a as an element of the natural numbers. So what I'm now going to do is take the limit of this sequence as a gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. So I'm going to now take the limit as a approaches infinity, because this looks awfully hopeful for this, basically. So the limit as a approaches infinity of this thing here, of the sum from r is equal to 1 to a of the modulus of x m r minus lr to the power of p, we're going to take the limit of that. Now, on the other side, we have that all of the terms of this sequence. So for whatever a you pick out, the sequence is now this, the whole thing. It's a sequence varying with a. So you can let a equal 1, you can let a equal 2, you can let a equal any natural number you like. We are now viewing it as a sequence, basically. So the first term of the sequence is when a is equal to 1. The second term of the sequence is when a is equal to 2. The third term of the sequence is when a is equal to 3, etc. It's a sequence of real numbers. In addition, it's a monotonically increasing sequence of real numbers, because the bits that you're adding on each time are non-negative real numbers. So this sequence can only get bigger or stay the same, basically. So what we do know, however, is that it's always less than or equal to eta over p, and that implies that the limit of this great big sequence also has to be less than or equal to eta over p. It cannot converge on anything greater than eta over p, basically, because that would imply that at some point, for some a, it crosses this boundary, basically, and we know that for all a, it doesn't cross this boundary. It never gets beyond eta over p. Okay, right, so now what we can do is just replace that with that series there, that limit of this series, the definition of that. When you write the limit as a approaches infinity of the partial sums, that just means the sum from r is equal to 1 to infinity, or moreover, the sum from r is equal to 1 to infinity actually means this. So of xmr minus lr, what we're guaranteed is that that is going to be less than or equal to eta to the power of p, providing that m is greater than or equal to n eta. So providing that this m that we chose here is greater than or equal to n eta, then this is going to be true. Now all we need to do is take 1 over p on both sides. So we raise both sides to 1 over p, and we get the sum from r is equal to 1 to infinity of the modulus of x m r minus lr to the power of p, all to the power of 1 over p, is now less than or equal to eta. Now you would have been thwarted. You would have been thwarted if you got all this way, and you hadn't done that trick at the start by redefining this eta so that eta was strictly less than epsilon. So we chose an epsilon for which we wanted this criterion to hold. We then said, okay, whatever that epsilon is, I can always find you some eta that is less than that but still greater than 0. So now we apply that trick. We say, okay, this is less than or equal to eta, but eta is strictly less than epsilon. So that implies that this sum from r is equal to 1 to infinity of the modulus of xmr minus lr to the power of p, all to the power of 1 over p, is strictly less than epsilon. I.e., we've done what we wanted. I have found you your big N, basically. If we now set this big N here that we needed in order for this convergence criterion to hold, if we now set big N to equal this big N eta, basically. So big N eta was this thing that we got from the Cauchy criterion on this sequence of sequences, whereas big N is the thing we're now using to imply convergence of this sequence, basically. Okay, so to summarize the argument that we had this sequence of sequences which we were trying to prove that if this sequence of sequences was Cauchy, that implied that it had a convergent limit. What we firstly did is we showed that if it's Cauchy, it implies that all of the term-wise sequences are also Cauchy sequences of real or complex numbers. Now, because the real line or the complex plane is a complete metric space, that implies that those sequences of real or complex numbers have limits. So the sequence of sequences does indeed have a point-wise limit. So all of the term-wise sequences do have a limit. So we can construct a sequence L, which is this sequence of all the term-wise sequences. So L1 is the term-wise limit of the sequence of first terms. The term L2 is the limit of the sequence of second terms, etc. So you get a sequence like that, and what you then want to prove is that the sequence of sequences does in fact converge to that sequence in the metric space LP. Okay, we haven't yet proven that this sequence is in LP. We'll do that in the next video. But to prove that the sequence of sequences does in fact converge to that sequence of term-wise limits, what we do is we say, okay, let epsilon be greater than 0. I want you to find me some point in this sequence of sequences such that if you take any sequence beyond or equal to that sequence in the sequence of sequences, then the distance of that sequence from this limit, or from this sequence of term-wise limits, is going to be less than epsilon. So firstly, what I say is, okay, epsilon is some number greater than 0. I can find you an eta greater than 0 that is strictly less than epsilon. I then say, okay, because of the Cauchy criterion, I can find you a point in the sequence of sequences, which is n big eta, which is an element of the natural numbers, such that if you pick any two sequences, little m and little q, which are greater than or equal to that n big eta, so the two sequences xn and xm are beyond or equal to that sequence x big N eta, then the distance in the LP metric space between that sequence x little m and x little q is going to be less than epsilon, which means that the summation from r is equal to 1 to infinity of the modulus of the rth term of the nth sequence minus the rth term of the qth sequence to the power of p, and then sum all of that up over r is equal to 1 to infinity, and then take the 1 over p of that is going to be less than eta. So I then say, okay, what I want to show is that if I take the limit of that sequence, it's still going to be less than eta is what I want, but I can't do that directly because of the trouble with interchanging the order of an infinite summation and the limiting process. So what I do is I break it down to a finite summation process. I then show that I then take the limit as q approaches infinity, and show that for a finite portion of that sum, the limit condition that I need is satisfied, and then I say, okay, it worked for any a, is an element of the natural numbers, so I spread it out upwards, and said, okay, that implies that it holds for all of the, for the infinite sum as well, and basically what I got is that the infinite sum from r is equal to 1 to infinity of the modulus of xm r minus minus lr to the power of p was going to be less than eta to the power of p, which implies that it's less than or equal to eta to the power of p, which implies basically that the distance between the nth sequence and the sequence of term-wise limits is in fact going to be less than or equal to eta. So then I just apply the fact that eta was in fact strictly less than this epsilon that I wanted in the first place, and then everything falls out. In the next video, we'll just demonstrate that this sequence of term-wise limits, this L sequence, is in fact an element of LP.